Thank you, Colin, for that introduction. Can you hear me okay on this? Thanks very much. Hopefully my slides will come up in a second. So I'm talking about cyborg experiments. So it's very much a practical set of experiments. Cyborg, as you know, there was a well-known documentary film a few years ago that some of you probably saw, called The Terminator, and in that cyborg was defined as a cybernetic organism, part human, part machine. So it's a little bit broader. It's not just the human-machine link, it's the biotechnological link, but it's very much experiments in that sort of area. What I'm not going to do is talk about this person's doing this work here and that person's doing that work there. James Moore in the audience is much better at me at doing an overall view of what's going on. All I'm going to talk about is my own experiments. I think they're quite cool, and I hope you do as well. So the first experiment I'm going to talk about really goes way back in time to the last millennium. In the mid-1990s, various people, such as Ray Kurzweil, some of you may have heard of, was saying in the future we won't need passports and we won't need credit cards, we won't need keys for our cars. What we'll have is a little implant under the skin that identifies us to the system around us. But nobody had actually tried it. I've put here class 2 implants, and I will explain what that means in a second. But in 1998, this is a younger version of me, and this is just my local doctor, and what he was doing was implanting in my left arm this thing, not the thing on the left-hand side, I have to say. We still have that strange currency in England at the moment. But the thing on the right-hand side is a radio frequency identification device. James was talking yesterday, for those that were there, about the very chip, which came along just after. This, is a bit bigger than that, but the very chip was the more commercial end that appeared a couple of years later. But this I had implanted. What we got it to do, just to show what's possible, was when I walked around my building in Reading, the computer in the building could pick up where I was at different points. So in the door frames we have big coils of wire, and they with current, electric current passing through them, and this device picks up current, so it's mutually induced current, which is used simply to transmit a signal back to the coils in the door frame. So the computer knew it was me and knew where I was at different points. So when I went down the corridor, the lights came on. Coming to my laboratory, the door opened automatically. Coming in the front door, it said, "Hello, Professor Warwick." I mean, it was fantastic fun. Various people criticised me and said no one's ever going to want to have anything like this in the future. But now, as Colin knows well, he's a regular participant at a nightclub in Barcelona called the Bayer Beach Club. There's another one in Rotterdam. I'm not sure whether, do you use that one as well, Colin? Or yeah, one is regular there as well. But you can't just get access to the nightclub. They send you round the corner and inject the very chip, the smaller version of this. And then you go back into the nightclub and you get access to particular areas. You should try this. It's good. It's like a fashion item, really. James, you've got to do this. And then you get access to particular areas, and they don't charge you cash. They simply scan your implant, and that's how you pay at the end of the night for all your drinks and things like that. But several people, has anybody got an animal, a cat or a dog, with a chip implanted in them? Anybody? There are some. There's at least one person. I mean, you may know cats and dogs. For you, sir, you can rest assured that this was fully tested on humans before your animal had to experience it. In 2004 in the US, the FDA okayed the use of a smaller version of this for people with epilepsy and diabetes, but that's been recently changed. This is it's the only words on the slides today, but this is regulation now that's coming in. This is from the Obama healthcare. So this is the present president. And the device is now, if you do have diabetes or epilepsy and you have one of these chips implanted, now you have to register it. You can't just have it implanted. There is a national registry, but the wording of the regulation is quite fuzzy. It really is very vague to the extent that if you have diabetes or epilepsy and you want state help or US help, if you like, then you may well in the future have to have something like this in order to be registered. So it's opening, it's very fuzzy wording, and where it goes from here, different people looking at it are questioning the, you know, whether the government in the future will be able to force implants on people if they want treatment. Okay, if you don't want treatment and you do it yourself, then it doesn't matter. But if you do want treatment, you may well have to have this device at some time in the future. But it's very fuzzy. The lawyers have probably thought it out. Whether this is a cyborg or not, I don't know. Arms up in the air. So let's go on to number 2. This is looking at one of the limits of being a human is that we have a very limited sensory input. I mean, we really are pathetic, the number of senses that we have in comparison with all the different signals that are out there. So the possibility of enhancing our sensory input is a key driver. And this is what some of my students are doing. So if there's any of you here that maybe you don't want to go all the way to have a neural implant, but you quite fancy trying something, then perhaps this is what you can try. I have 3 students at the moment who have magnets implanted in their fingers. So these are little permanent magnets implanted in fingers. And you'll see this is the Jowish, one of the students, having the implants in. Colin, you should try this. You know, it's only little magnets. It's no problem. But we have to get ethical approval from the university to do this, which is not surprising. Putting things in students' bodies could be difficult. But if you look at the picture here, you'll see that the guy that's doing this has tattoos on his arm, and that is because he is a tattoo artist. That's his job. He's not a doctor at all. But this presents us with problems, because on the ethical approval forms for the university, there is a line which says who is carrying out the medical procedure. Now this guy that does this in the UK, he goes by, it's more of a trade name, but he goes by the name of Dr. Evil. Now, as you imagine, this is an enormous problem. Who is carrying out the medical procedure? Dr. Evil, and then the committees just go berserk. So it creates also, he's actually a good guy, and if any of you go, he knows what he's doing, and so on. This is what we're doing. You can see the magnets, 2 magnets implanted. And as I say, I now have 3 students working with me that have magnets like this implanted. You can see it's the left hand, because if something goes wrong, it's not so serious. And we see from Jowish an example of sensory substitution here. On the baseball cap are ultrasonic sonar sensors. We saw there was a boat ride some of you may have gone on last night down the river. Lots of bats around. Bats use a sonar sense. Humans don't. Surely you must be jealous when you're looking at bats. You don't have to be. Now is a chance. And the ultrasonic sensors, the output from them is connected down. You see the little coil of wire. So a little coil of wire round the finger with the magnet in the finger. As an object comes closer, the current in the coil changes, and that vibrates the magnet. And as the object moves further away, the vibrations die away. So essentially, as an object comes closer, the person can feel with this magnet vibrating in their finger more and more, or less and less. So it's converting a sense of distance, because sonar can be very accurate in terms of measuring how far objects are away, a distance measure. It converts distance into touch, into a very close feeling, very accurately. Ian, not this student, but Ian, who's doing a PhD with me now, what he has done also is to take an infrared sensor and feed that in. Now, infrared gives you a remote sense of heat. So effectively there, as an object gets hotter, so Ian will feel the vibrations more. So he can feel, if you like, he can point and say, you are hot, you are not so hot, you are, I mean, not in a sexual sense. I mean, that would be a really good sensor, but just in a pure temperature sense, it's a remote detection of heat, which of course humans don't, unless there's somebody here, you know, a superpower person, humans don't tend to have that. Now this of course has immediate military applications, because if you can imagine a soldier with one of these devices, a little infrared detector on their finger with a magnet, before they go into a room, if they don't know whether there's anybody in a room, they can just put their finger around the corner of the room and simply scan in the room. Ah, there's somebody over there. Yeah, there's somebody over there. So they would know pretty accurately where the people were in the room, and they would also know how hot they were. I don't know whether that's any good, but there's uses immediately. Ian also at the moment is feeding in different audio signals to, if you like, with people like Beethoven, it's said that he could feel the music. He couldn't hear it, but he could feel it. Well, we're actually experimenting on that in this touch sense, so feeding in different frequencies to do with music, and then seeing how long it takes Ian in this case to determine what the song is, what the music is, and so on. Of course, with that, if we want to write it up in academic papers, we're going to have to use Beethoven and Mozart and people. If we use some pop stars, then of course the papers will never get published, because pop music isn't listened to by intelligent people, so I'm told. This is a student called Ashley. He won the Best Project Prize. Some of you may recognize the work. This is originally done by a guy called Paul Bacchi-Rita, brilliant scientist from a few years ago, and what he did was try and communicate signals via the tongue. So this is for people who are locked in or have difficulty communicating. It's to try and send signals in to communicate via the tongue. And you see, Ash, this was the prototype, a small array where current is small pulses of current are sent into the tongue. So this he puts on his tongue and send different patterns. We're able to try it out with lots of different students, with ethical approval again, of course. And what we found is, first of all, it's very, very quick. If you try this, you can learn to recognize letters and patterns very, very quickly. Secondly, it's a very quick route up into the brain. When you stimulate on the tongue, very quickly, very rapidly, the brain can recognize the pulses, much more quickly than the visual input, which is relatively slow. As far as we're aware, although the optical nerve and the auditory nerve have been fairly well studied, the route in from the tongue is not really well studied medically, and this rapid route is an interesting one. The other thing that we found, I'll just share this with you, I've no idea what it means. If he stimulates, say, a little triangle shape, and we ask the person, what is it you witness, they will say it's a triangle shape. That's what they witness. But if we ask them to draw the shape, some of them will draw it the same way up that we're stimulating, but others may draw the triangle upside down or sideways. and we really don't know what this is. It's like a hard wiring from the tongue to the brain, and it seems to be fixed in a certain way, because no matter how much we try and train the person and say, look, this is the pattern, give them a visual input or some other way, but they still stick with the same relationship. So maybe in years to come somebody will produce a paper, say, oh, look what I've found, and you say, oh, I've heard this before. But if they have some scientific results or evidence to back it up, because we don't, it's just an observation at the moment. This is the sort of fun observation you get with this sort of thing. The next type of cyborg I'm going to move on to, culturing neurons. This is taking brain cells and culturing them, growing them, and putting them in a robot body. But first of all, I just want to introduce you to some of our robots, because in my normal working life I get to play with quite a few of them, so it's good fun. What you're going to see first of all is a robot head called Morgui, which is, I mean, there's a Mandarin Chinese for magic ghost, a bit scary. And the next robots, the little wheeled robots, are the ones that are more important to this presentation. This is taken from a BBC program called Inventions That Change the World. And I'm going to try, hopefully the sound is working. We may have to start again if the sound doesn't work here. So here we go. Can you...
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher...
Yes.
Where are these in terms of... Are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor,
if we turn off this section,
was here,
they have a basic instinct to go and look for some power somewhere else. They will keep going to do that until they find some.
So if I put him down,
it should go off.
So we'll have to go and look for power. Are you going to tell him to do that?
No, it's an innate response for that robot. It's a basic thing of its life. Yeah.
No, his lights have come back on.
Lights have come on.
So he's found power.
He's happy now that it's getting power. Away to go.
But these then are as intelligent as slugs.
It's different. But in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
I have to say, I know none of you ever use Wikipedia, but if you did, the original quote from that was that our robots have 50 to 100 brain cells, which make them about as intelligent as a slug or a snail or a Manchester United supporter. But the BBC didn't like that bit. I've no idea why. Those robots actually have microprocessors for brains, and we can get them learning and learning how to avoid hitting each other and objects, get them communicating with each other, so teaching each other, all sorts of fun stuff in the artificial intelligence area. But what we've done now is replace the computer brains that they have with a biological brain, which I will explain. So if we look on the right hand side here, dans la droite, is it? Oh, terrible, that's it. That's about it, I'm afraid. On the right hand side, the physical body of the robot is what you were looking at. Its wheels are easier than legs for what we're doing here. Ultrasonic sonar sensors, again, that's the physical body of the robot. The left hand side, it says biological neural network. So we've replaced the computer with a brain, a biological neural network. MEA is multi-electrode array. So what this is a little dish with electrodes on the bottom of the dish, and we take brain cells, typically from rat embryos, separate the brain cells, the neurons, using enzymes, and then squidge them in this dish and feed them. They have to be fed with, it's a little pink liquid with minerals and nutrients in it, very much like an energy drink, the Gatorade or things like that. Very, very similar, except that this costs a lot more because it's in a special laboratory bottle. Every couple of days we feed them. It has to be kept in an incubator at 37 degrees centigrade, although more on that later. This is what it looks like. These are, the black rings are called Potter rings, after Steve Potter at Georgia Tech, who developed them. What they're for is to try and stop the brain dehydrating. We have to keep it moist. This is a living brain. The neurons, it's quite amazing when we put them there. We can look under the microscope at what they're doing, and within the space of 20 minutes, so very, very quickly, the neurons are putting out tentacles, what look like tentacles, and these tentacles link up with each other. So if the neurons are very close together, they will link up and become the dendrites and the axons, the inputs and the outputs of the neurons. And then over time, the neurons further away will connect. So it's very non-linear. Some of the neurons are bigger than other neurons. Neurons, as you know, if you scoop out some of your brain cells tonight, you'll see some of them are maybe 2 micrometers. That's the sort of smaller size, up to about 20 micrometers. That's a sort of typical size for brain cells or nerve fibers. So that's what we're looking at in that dish. The typical brain for us will have about 100,000 brain cells. So it's not up to the human 100 billion. It's nowhere near that. But 100,000 is okay. It can be a bit more than that, but that's the typical figure. After about 10 days, we have it's a 2-dimensional brain. It's quite complex, and we can connect up to it. These electrodes here go into the central area of the brain, as it were, and we can either send signals in to the brain to stimulate it, or pick signals up from the brain, to do both. And we will pole around here, try stimulating at different electrodes, and see when we get a reasonably rapid response within a few milliseconds from other electrodes. So our signal's going in, and if you like, the brain is thinking about it and then providing an output. We will then link that to the robot body. So the sensors, ultrasonic sensors from the robot, will stimulate the brain. The output from the brain will change the direction of the robot. So what you're going to see now, this is it's a baby robot. The brain is at most 2 weeks old, maybe about 12 days old at the moment. And what it's supposed to do is move towards the wall and turn right, which you're going to see now. Ta-da! That's what it's supposed to do. What it's not supposed to do is change its mind and turn round and then crash into the wall. But this is a baby robot. It's got to learn. This is just its first day into the corral, and we'll see. Some of the time maybe it's a bit premature. Again, it turns round, off it goes. Yeah, did it right, great stuff. Gets it wrong again. Now, we can look under the microscope, both in real time at what the brain's doing, but also over a period of time, because this brain is in its body for about 1 hour every day, and every day, literally. So we can look at the neural development. So as it does this, day after day after day, we can witness the connections between the neurons in certain pathways strengthening. And we can also witness how it changes its behavior. This is a process called Hebbian learning, habitual learning. One neuron fires, another neuron fires. Every time that happens, the connection between them strengthens, and it physically strengthens. And you have to remember, this sort of thing is going on in your brains all the time. If you do something, you do something, you do something, every time you do it, it makes it a little bit more likely that you'll do it again, which is the problems we have with habit forming and that. And we can look at that happening under the microscope. So now I'll skip forward. This is the same robot with the same brain after 2 months. And that's all it's been doing, is that. So you'll see how the brain has developed. Now, one reason we're doing this research is to try and figure out how memories are formed in the brain. How the robot memorizes, this is the situation I'm in, and what do I do? So we see here it turns. Now remember, this robot has had a university education, which in the UK now you have to pay fees for a university education. So we're expecting our Vice-Chancellor to start charging a special rate for robots, maybe more for international robots than EC robots. This one is a bit boring. It does it okay all the time. Some of the other are more hesitant, some of them will still be a bit awkward, do their own thing, but this one, I think it just goes through the routine. But you can see the difference. This is after 2 months habitual learning, and the robot now has changed its behavior in a very simplistic form, a very simplistic way. We're now working with a group in Canada to develop, rather than growing them in 2 dimensions, we use a lattice structure to grow in 3 dimensions. From my point of view, this is great because it increases the number of brain cells to something like 30 million. So that's point 1. So we're looking at 30 million brain cells in a robot body, not just the 100,000 that we've been working at the moment. The other thing is we also have human neurons. I was surprised how easy it is to get human neurons, but it literally is. Can you send me some? And they turn up next day. So we're looking now realistically at 30 million human neurons in a robot body. That's where we are now with the technology. Clearly, as the technology develops, more electrodes, larger arrays and so on will mean that number can increase. And clearly, okay, at the moment we can use it for medical research, figuring out how memories exist. Can we improve them with stem cells and more neurons, that sort of thing, and hence maybe tackle Alzheimer's disease, dementia from the bottom up. That's the hope there. But clearly from a philosophical point of view, if we have not just 30 million, but let's say 100 billion human neurons in a robot body, then we have to ask all sorts of questions. This robot would have a brain that is the same size as yours and mine in terms of numbers. According to John Searle, one philosopher, the brain would be conscious because it's human neurons and consciousness emerges from human neurons. And should I be able to switch it off when I go, or should I be able to throw it in the bin when I go home at night, or will it want to switch me off or throw me in the bin when it goes home at night? we have to start asking all sorts of questions. Should we allow it to vote? And if it votes for the person I want, is that okay? And if I make 20,000 of them, all sorts of questions. So if you do know any political people that wish to fund this research because they want to be re-elected, then fine. Berlusconi excluded, I think. There we go. That's enough political statements for one day. The next thing I know some of you are aware of, this is a medical procedure commercially available now, but I want to add something on to the end of the presentation, particularly for Parkinson's disease, but also epilepsy, Tourette's syndrome, even clinical depression. Deep brain stimulation is used to counteract the effects, and I'll show a video of it to show what's possible. The electrodes, I mean, they drill a small hole down into the center of the brain, typically the thalamus or the subthalamic nucleus, more likely, and along the end of the wire there are 4 or 6 electrodes. The surgeon then selects which of the electrodes is best and uses that to provide a stimulating pulse. So what you're going to see now is a video of somebody who has Parkinson's disease, and you'll see how awful the disease is. They've received the 2 electrodes in their brain, and this is something you may have wondered. I'm sure if any of you are into the human body and how it is, you may have wondered why we have all this space here. There's not really anything in the way of organs or anything here. Well, it is a wonderful part of the process of evolution, because what this space is for putting pieces of technology, and you will see the power packs for the stimulators are positioned here, and then there are wires running underneath the skin into the electrode. So this is a genuine person with Parkinson's disease, and you'll see how he is with the disease, and then when the electrodes are switched on. And we go on to the sound again for this.
I'd like to show you in 2 minutes what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery, without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted in the electrode into his subthalamic nucleus, which is a tiny part of the brain, and you see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he reset himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer, does he say? And we'll show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, This stimulator works very well. Many people benefit from it. One problem it has is that it's providing current all the time, and the power packs get used up. And recharging is simply not a realistic operation as far as, having implanted power packs that can be recharged externally for a number of reasons. One is the patients don't want it. The surgeons we work with, Tipu Aziz at the John Radcliffe Hospital in Oxford, doesn't implant any rechargeable batteries, partly because they're not very good and people don't want it. What we're doing is working with him and his team to make the implants intelligent. So rather than the power packs being used up and the person having to go into hospital every 2 years to have an operation to have the power packs replaced, which is what happens at the moment, we want to get the stimulators just to stimulate when they need to stimulate. In order to do that, they need to know when they need to stimulate, and hence we are recording electrical activity from the subthalamic nucleus that we're measuring via the electrodes, feeding it into an artificial intelligence system, and then getting that to learn, first of all, to recognize the electrical activity in the brain with when the tremors actually start. That's the first point. But artificial intelligence systems of this type can also predict. And what we've found is that the system can predict up to 15 to 20 seconds ahead. So what I'm saying there is electrical activity is being monitored by an artificial intelligence system that is effectively modeling that part of the brain to an extent. It can then predict from that electrical activity 15 to 20 seconds ahead when the tremors and the muscle locking is going to start. And so what we're doing now with the surgeons is providing a feedback loop. When the artificial intelligence system raises a flag, say tremors are going to start, then the stimulator will be applied and not before. And that's what we're working on at the present time. So partly it's using AI to outthink the human brain, if you like. Now, most of that is therapy, and I'm sure for all of you the most important thing is enhancement. It's pretty awful being a human. We're really limited in all sorts of ways mentally, so why not upgrade? And a few examples we know from science fiction, and maybe if you can remember, extra memory would be lovely. Senses, the third one down, we've seen some examples of that. Extend your senses. Multi-dimensional thinking is an interesting one. The human brain thinks in 3D. Computers can think in hundreds of dimensions, so why not think in more dimensions if you want to? Communication for me is a real big one, because when you compare how humans communicate in comparison with technology, frankly it's embarrassing how we're awful, we're terrible. When you think there's highly complex electrochemical signals in our brains, thoughts, images, feelings, emotions, all sorts of things, and if we want to communicate those to somebody else, what do? Well, we convert those highly complex signals to trivial coded mechanical pressure waves. That's what I'm doing now. Mechanical signals that are very, very slow. They eventually will get to you. Your ears will convert them back from mechanical signals to electrochemical signals. And even if you've been married for 40 or 50 years, you still have no idea what it is your husband or wife is trying to tell you. Why not? Let's upgrade, let's enhance, let's start sending signals from brain to brain in parallel. Also, let's communicate with emotions and feelings and images. It will completely change the education system. Perhaps we can do away with this silly thing called examinations, save ourselves an awful lot of time. So that's the sort of direction we're heading. But it's difficult to decide what is therapy, what is enhancement. This is Campbell Aird. He lost his arm due to cancer, and he's been given this robot arm. But you see him with his human hand. He flicks the switch to operate the robot hand, and he'll do it again, flicking the switch, which is crazy, really. We want him to operate the robot hand directly from his brain. and to feel what the hand is feeling in his brain, surely. So it's another hand for him. That needs a bidirectional interface to get signals from his brain onto the wires and signals from the wires into his brain. Let's assume we've got it. Let's assume we're there, because then we can look at Campbell and other people like him, and as long as we have mechanical arms and legs, we can give somebody replacement arms and legs that they control from their brain. But, now this is the nice bit, we're talking then about brain signals on wires. And once we've got brain signals on wires, we can clip onto those wires and send the signals wherever we want. You don't have to have brain signals, neural signals, just in your body. You can have your brain signals going across the internet and having bits of your body on other planets, on other continents, wherever you want your body to be, that you can have as long as it's networked. So now with the this is not way off into the future. This is saying now, if you want to have your brain in one place and parts of your body somewhere completely different, fine. The technology is there to do that now. So what have I done in terms of projects in that area? This is a clip from BBC News.
Now prepare yourselves for this. A British scientist has become the world's first bionic man.
It's true. Cybernetics professor Kevin Warwick has had an implant attached to his nervous system. We'll have a look at it in a minute to discover exactly how the brain sends out signals controlling movement and even sensations such as pleasure and pain.
The secret operation involves surgically inserting an implant and cable into the left arm of Professor Kevin Warwick.
Well, the operation's been going about 10 minutes now. Spoken to Kevin, everything's going fine from his end, and the implant will shortly be about to go in.
The implant was fired onto a main nerve near the wrist. Wires from the implant were then threaded through a cable beneath the skin, exiting further up the arm to an electronic connector.
Effectively what we've got is a link from my brain down the median nerve, through the wires and out to the connector. And then in the weeks ahead we'll be putting on our radio transmitter receiver that we've developed at the university, and that'll be making the link by radio from my nervous system to the computer and back the other way.
This is what everyone hopes to see, nerve signals resulting from finger movement or even emotions. The medical aim is to help people who are paralysed, although some experts are unconvinced. But Professor Warwick is used to detractors, and experiments linking his nerves to a computer will begin soon. Sue Nelson, BBC News.
So, what actually happened? Well, this was again at the Radcliffe Hospital in Oxford. 2 hours of neurosurgery. This was a research project for the surgeons as well. And what they fired into me was this little thing. This is called the Utah array. It's also known as the brain gate system. And this was fired into the median nerves of my left arm. Each of the spikes are about 1.5 millimeters long, and literally it was fired in, and the median nerves in total are about 4 millimeters in total, so the spikes went in about halfway. The electrodes themselves typically are about 2 micrometers in diameter, so they're the same dimensions really as nerve fibers or neurons. So you're getting down to the possibility of stimulating or measuring from individual neuron nerve fibers or just a small bundle. Sorry if you had a lot for lunch, but the record, I have to say, is Trinity, Cambridge. We had 4 students faint when I showed this picture, so you guys are doing all right at the moment. That's Cambridge for you, they can't take it. This is my left arm. What they had to do was to make 2 incisions. They then pushed that tube down between the incisions, and that array of 100 electrodes they pushed down the tube They then removed the tube altogether, hammered the electrodes into my nervous system, and I then had wires running up the inside of my arm. You see the surgeon holding the little connector pad. So that for 3 months, that's how I was with the implant in my nervous system, and we could pick up, when I opened and closed my hand, pick up neural signals on those electrodes. So it was like externalizing my nervous system. So either could open and close my hand and we use those neuro signals to operate technology, or we could stimulate my nervous system, and it took me 6 weeks to learn to recognize the different pulses. I've now got a clip from Discovery to show some of the things I was able to do.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralyzed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman.
So, a little bit of Nietzschean philosophy. Couple of holiday snaps to finish with. This is me with ultrasonic sensors, a blindfold on. My brain was receiving pulses of current, as I described before, that increased in frequency the closer an object came. This is via the implant in this case, so I was able to move around and detect pretty accurately where objects were. So if you want an extra sense, certainly an ultrasonic sense, if you want an extra sense, put your name down and go for it. It's there for you. This is my wife talking to someone about the Royal College of Art in London. A student of the Royal College of Art put this jewellery together, and the jewellery changes colour from red to blue. It was linked to my nervous system. So the best way of thinking about it, when I was calm and relaxed, my wife's jewellery was blue, and when I got excited, my wife's jewellery started flashing red. She works in a completely different office to me, so if you can imagine, there she is in her office, the jewellery is blue, fine, he's not doing anything he shouldn't, and then the jewellery starts flashing red. What is he doing? And more importantly, who is he doing it with? So maybe not such a good idea. This was in Columbia University, New York, where they filmed Ghostbusters, I believe, but they do also do some research there. And what we did was link my nervous system with the internet and link it up to the robot hand that you saw before with Campbell Aird back in England. So when I moved my hand in New York, my neural signals went across the internet to move the robot hand. When the robot hand gripped an object, signals were sent back from the fingertips to stimulate my nervous system in New York. So I could feel how much force the robot hand was applying on another continent, essentially extending my body across a network. And then the final part of the experiment, you can try this tonight if you've got some time. Just put some electrodes into your nervous system, and you will find it is extremely painful. My wife had this. It's microneurography. We went to the doctor to have it done, and we thought he was going to give us some anesthetic, but he said, no, I need to make sure I've made a good contact. So he pushed the electrodes in, and she screamed, and the doctor said calmly, I think we've made a good contact there. He pushed another electrode in, we went back to the lab and electrically linked our nervous systems together. So every time my wife closed her hand, my brain received a pulse. So literally tick, 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 and my brain got tick, 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 3 pulses, and back the other way to stimulate my wife's nervous system. So it was communication directly between our nervous systems using telegraphy, a bit like the Morse code. So very, very simple. But clearly where we're going with this is not just nervous system to nervous system, but brain to brain. I have to say, just to conclude, that my wife doesn't like the idea of having a brain implant. I can't understand why. So, but I'm definitely on for it. So if there's anybody in the audience that would quite like to join me, is happy to have a brain implant, please let me know. Thank you very much.